Okay, good. Thank you very much. No, again. Good. Thank you. Thank you. Okay. I think we should start. Thanks for coming. And today I will talk about the AMO and AMOC. We know that in the Atlantic Ocean, the two most important climate features on multi-detail time series. One is the AMO, another is the AMOC. So today I will try take a look at the relationship between the AMO and AMOC. Of course, it's from IPCC model because observation is so short to do the AMOC, only about 10-year observation. Here is the outline. First, I will show in the IPCC CMAX 5 model, the variability was 8 AMO. And second, I will show AMOC variability in the CMAX collect model. And then next topic, I show the relationship that here is something new over here. So before, people only emphasize AMOC influence on the AMO. However, my research emphasizes interaction because AMO also can influence AMOC. This is the new result. And the last one is about impact. Impact, what I focus on here is on the global model bias. Because IPCC report, we know that IPCC, when it come out, most of it depends on model result. Here I will show the common model bias for the IPCC model. So question, do we believe the IPCC model prediction and the projections? Okay, so what is the AMO? The AMO is a of course, from name you see the multi-decadal variability. The top panel shows the AMOC index, which basically is activity anomaly over North Atlantic from equator to the north of the 6 degree north from east and west. And the shading is the low pass filter, which is a 7-year long mean, which basically removes the interannual variability. We keep the multi-decadal variability. The low panel shows the regression of the global SIT onto the AMO index. We see that the AMOC signature is on the global ocean. So particularly in the North Atlantic, okay, we know that the AMOC will have warm water. However, in North Pacific, it's also warm together. And another most important feature is over South Ocean. Some PhD scientists focus on South Ocean. Over there, the AMOC also shows the cooling over there when the AMO is in positive state. Okay, so how the model perform? So here, so this my cell phone? No. Somebody else, okay. So this figure shows 27. If you make a more model, it's similar result. The color, you see the color curve here shows the different individual model. And the black dashed line is the ensemble mean for the 27 model. And the solid curve, which, so basically if you're starting from the last 20 years, okay, from last 20 years, you see that the model did a very good job over last 20 years. However, if you take further, for example, take down here, the model not good. So model basically disagree with observation in both phase AMO and stronger AMO. And particularly if during the observation, you see the observation during the early 20th century, that the ocean is cooling over there. However, model underestimate this cooling. Also, during the mid-century, that the observation shows the Atlantic Ocean is warm. However, the model also underestimate this is a warming feature. This is the model. Here I should.
Will FST remove just residual or just include?
You mean this? We remove the linear trend. Yeah. Then we perform the we calculated the power spectrum of the AMO index. I just showed in last slide. So you see that observation is a black solid curve, this curve. So basically we show peak at 70 and also over 40, 25, and 10 years. So we have 4 peaks for the observable AMO. And the model, you take a look at the ensemble mean, shows the 70, 40, and 25 peaks. However, the most model cannot capture the 10-year peak, which means the IPC model, most model cannot do the 10-year oscillation on the AMO. And here is the spatial pattern of the model result. Again, the first panel is observation. So you basically see the observation show here that when AMO in positive phase, the whole Atlantic Ocean is warm. We know that. And but one feature I want to point out here is because later on we will use this. You see the largest positive axis is in high latitude, not compared with low latitude. This is much larger. This is very important because later on when I study the mechanism, this will use this feature. So this is very important. And the model also shows the weak warming. If you compare with the observation, each model shows the weak, especially in tropical regions. Look that the model is not too good. Okay, this is a spatial pattern AMO. And then we talking about the Atlantic Ocean. This is from another paper, which shows the mean circulation, ocean circulation, and atmosphere surface wind over the Atlantic Ocean. And here is north, and this is the equator, this is the south. So basically, on atmosphere part, on the equatorial region, we have a trade wind, and the wind is a flow inside our paper. On the middle high latitude, in middle latitude, the wind is the westerly wind, so it's a flow out of the paper. And in the ocean part, there are two circulation. One is the AMO here, this big circle. Another one is the so-called subtropical cell. And today I will not focus on this. And I have another paper which focus on the shallow subtropical cell, but today I will not mention this. Okay, so then we take a look at MOC for the climate model. So here is how to calculate the stream function of MOC. You see that show the different models show different results. So variability is a highly varying structure. However, the model captures the basic structure. For example, in the upper ocean, you show that this stream function is positive, which means the ocean water the flow from the surface from south to north, and at depth the flow southward. This is called MOC. And the model also captures another negative value of a stream function, negative value, and this is so-called Antarctic bottom water cell. So model basically capture both AMOC and ABW. Okay, then I also calculated the spectrum of AMOC indices. So you see that different models behave differently. So this is not surprising because this is ocean circulation. And the model also shows a large energy over multi-decadal time scale, much larger energy. And then we move to the mechanism. So in 2010, Sankey and I developed a mechanism for the AMOC, which this paper published in Journal Climate. So basically, this mechanism, we divide the Atlantic Ocean into 4 blocks. One is in low latitude upper layer, and another one is in high latitude upper layer, and the deep ocean will have another 2 blocks. And between the blocks, the water that transport, which is because the density is different between this block and this block. And if we consider the mass conservation, we can get this 4 equation. I don't want to go to detail of this equation. However, I want to show the solution of this 4 equation. So if we give a model parameter, here are the 2 cases. The delay time is 7 years, Another time, the delay time is 20 years. The model shows oscillation. However, oscillation is damped, like ANSO. The ANSO says that some models show damping oscillation. And this kind of damping oscillation means a high frequency fault, and people call noisy. If you put this model into the high frequency fault, the model will continue oscillate on the is not a regular oscillation. So physics for this kind of simple mechanism model, that the model have two feedback. One is the positive feedback, another is negative feedback. So this positive feedback, negative feedback interact together, the model can oscillate on the multi-decadal time figure, like ANSO. Every other few years in Pacific Ocean will have a El Nino. The next 2 years, 3 years, maybe we'll have another El Nino. The similar situation for the AMOC. The model can oscillate. So for simple way, we see that why this model oscillates. The simple way to see that is because the delay response due to the density gradient between the high latitude and the low latitude. So the associated with the AMO, the median density gradient is very important for this kind of model oscillation. Then this is a theoretical model. The question is a couple kilometer model has this kind of mechanism. So this is the purpose for our next step. So we analyze this mechanism in kilometer model. Okay. So here what we did here is the lead and lag correlation. So here you show the x direction. This is the delay and the lead year, unit is the year. So positive value means AMOC lead the AMO. Negative value means AMO lead AMOC. So if then we take a look at almost all model, not this model, not this one. This is the box I show here. That one common feature here is that when the positive lag, which means AMOC lead AMO, we have a positive correlation. What this means? This means this is very easy to understand. When AMOC is stronger, this AMOC will produce northward heating transport, then whole Atlantic Ocean is warm. So we have a positive correlation. However, if we go to the negative leg here, for example here, which means AMO lead AMOC, we have a negative correlation. This is also very important. So what does this mean? This means that when AMO lead AMOC, we have a negative correlation. Why this happens? Is because the AMO induce median gradient in density. So this is how. Remember in earlier I showed you spatial pattern with AMO. I show you the maximum SAT anomaly in the high latitude and the low small value in low latitude, because this warm SAT in high latitude and low latitude will produce the density gradient, which will further weak AMOC. This is why we have a negative correlation between AMO and AMOC. This is new. This is because during past people most believe this, and what we found is the second part. When AMO lead AMOC, we have a negative correlation, which can make the couple system oscillate or make AMOC oscillate on multi-decadal.
Yes, if I can ask, your AMO index, is that at a specific latitude or?
We choose I should say that. We choose between the 20 degree north and not 20 degree and 30 and 60 degree north below the 500 meter maximum stream function. We want to exercise subsurface because at the surface that wind drive ocean surface is very important. So we use the below 500 meter maximum stream function as the AMO index.
Anywhere between 20 and 60.
Yeah. Okay, so this is. Then we continue to perform another analysis, which is so-called the maximum coordinate analysis. I don't want to. This is the only mathematical tool. Okay, so it's a method that is not new. Many people use this. and perform AMO, AMOC together. Okay? The left panel shows the SAT anomaly. Right panel shows AMOC stream function. So, okay. So you see that the color is red, which means AMOC is positive. Positive means AMOC, Hamilton positive, which means AMOC is stronger. So when this happens, AMOC is associated with warm North Atlantic Ocean, which is the AMO warm phase. And okay, the low panel, what we show that warmer SAT in North Atlantic Ocean, the AMOC stream function is negative value, which means the AMOC is weak, so the correlation is negative. The consistent with our early calculation. So when AMOC leads, we have a positive correlation. When AMO leads, we have a negative correlation, which means AMO produce weak AMOC. Okay, so far we perform the couple several statistical analysis. What this analysis tells us? First, when AMO lead AMO, the stronger AMOC will produce warm AMO because of the increase northward hidden transfer. This is people normally believe will have positive correlation. So, however, what we found here new is after time delay, this warm AMO will reduce the median density gradient. Why? Because the AMO is associated with the different SAT warm in high latitude and low latitude. And this kind of SAT anomaly will reduce the median density gradient, which reduce AMOC. So the correlation is negative. And this process repeat and repeat, so the AMOC can oscillate on the inter-annual time scale. This is why some models show the oscillation. Okay, some models show 20 years, some models show 30 years, depending on model. And the key element in such kind of oscillation, either in simple model and climate complicated couple model, that the two feedback. One is the positive feedback, another one is a negative feedback. Because in a couple system to oscillate on the any time scale, you have to have positive feedback and negative feedback. Like ANSO positive feedback is the Berkeley feedback, and negative feedback is the ocean current with loss wave delay response. The similar situation for the AMO is positive feedback is this, negative feedback is this. Okay, so here's the summary. So basically the AMO and the AMO can produce a multi-decadal oscillation. What we found new here is the AMO also affects AMOC. And like the previous our view is AMOC own influence on the AMO. So here this is the cartoon, actually not the cartoon, this our analysis shows that when AMOC is stronger, the positive value is stronger, then this AMOC will produce the warmer SAT over Atlantic Ocean. You know, the high latitude will have warm water, low latitude will have relative small value. And this distribution of the SAT anomaly in high latitude, low latitude will produce the median density gradient difference, which will further weak the AMOC. So AMOC stream function become negative. So basically this is the whole cycle. And next topic, actually, I want to show the impact. This I already produced in AMO lab review. Basically, the paper published in this year in Nature Climate Change. So what we did is here. We used 22 model here. This is figure calculated. The ensemble mean of a global SAT by which means model SAT minus the observed SAT. And the data, you see the many data over there, which mean 80% model show same size, positive and positive. The data mean this. So our purpose here for this paper is that we try to assess, we try to calculate the common feature of the STP over global ocean, because if you see, okay, if you see this, you see, so your model is good for prediction projection. So here is the model by, it's very large. And the second, we try, okay, I use the word try because this is it's harder to see. This is the definite mechanism. We tried what caused this model bias. What possible, second question, what possible caused this global model bias? And last one, we focus, you see that model bias shows this, right? North Atlantic will have cold water, and North Pacific will also have cold water. So what caused regional, can this cause this? Is our third purpose. So okay, anyway, the common feature is over there, or Southeast Pacific, South Atlantic region. And this is the model by further model almost 20 years, past 20 year model. So right now we still have a problem. We did not fix the problem. So so basically this model by here and is a problem for the model. It's headache. To me, it's a headache. It's also not an easy problem. But here we argue, people argue this is only local effect. However, our paper shows it's not. I will show later on this bias can induce by this. Okay, this is it. Then, okay, this is we'll then perform another SVD, so-called singular value decomposition analysis. So this is another mathematical tool. So it's nothing important, just a standard. You go to textbook, you can find this method. We perform the STP by AMOC stream function together by this method. What we show here is the first mode, which is about 45% of the variance. So the top panel shows STP by. This panel shows AMOC stream function. And the low panel shows the time series of this STP by AMOC stream function. So you see this pattern is very similar to the last slide I showed you. The North Pacific is cold, and the North Pacific also cold over South Ocean. We have warm STP by. And the corresponds to this pattern, the ocean shows that AMOC that the value is negative value, which means the AMOC is weak. And you see, I also have a positive value here. This is ABW, Antarctica bottom water. So we have a positive value, which means this is stronger. When global STP by increase, AMOC is weaker, and ABW is stronger. Then, okay, next we try to use the, as I said earlier, the global model by shows cold by in over North Atlantic Ocean and cold by over North Pacific. So we try to get a relationship between these two by first. So why, not the question, why North Atlantic and North Pacific show similar by? One by, if you Pacific, your model shows the Pacific is one by, in North Atlantic also is one by. If the cold by both are the same size, so we try to answer this question why. So in order to answer this question, we first take a look at the AMOC. We saw this AMOC problem. So this top panel shows this relation between AMOC and STP by over North Atlantic Ocean. You show that when AMOC is weaker, the cold by become larger. The correlation very high, about 8.5. And the low panel shows the relationship between STP by in North Atlantic Ocean and the North Pacific Ocean. So the correlation also is positive, which means when North Atlantic is cold by, North Pacific must be cold by. If North Atlantic is warm by, North Pacific must be warm by. So question why? Why did it happen? Why did it happen? So okay, so in order to answer this question why, we perform the intermodal EOF analysis over North Hemisphere, which includes the North Atlantic and North Pacific. And top panel shows the spatial pattern, lower panel shows the time series of the first mode and compare with the AMOC index. Red color is the AMOC index. So basically, when North Atlantic AT is coded by is negative, the North Pacific AT bar is also negative. The correlation with the AMOC is also negative, very high correlation. So, conclusion here is that a weak AMOC can cause code by in North Atlantic Ocean, which is associated with a code by in North Pacific. So first part is easy to understand. When your model AMOC is weaker, which means the northward heat transport is smaller, so the whole ocean will be cold. Okay, this is easy to understand. This is also our normal understanding for this. However, why this connect with this? So this is the next question we try to answer in this paper. So what we did here was, okay, we have a PC mode last P time series, right? Then we make a calculation regression of the PC1 mode onto the shear protection height at 200 millibar and the sea level pressure regression. And this is the surface wind shear. So you see that the pattern, you see the similar to the North Hemisphere annular mode, which is this is the first proposed by global people in University of Washington long time ago. And, so people know that. And if you see the pressure, sea level pressure, you see when negative pressure in North Atlantic Ocean and North Pacific also have a negative sea level pressure. And surface wind shows strong westerly wind normally over the North Pacific. So what does it mean? Because over this region, the mean state of wind is the westerly wind. So this wind anomaly were stronger the westerly wind. So the westerly wind will intensify. So this intensified wind over this region have two effects. One is including the latent heating flux, which will cool the ocean. Second, this westerly wind anomaly will produce ocean advection by Ackermann transport, which also advance cold water from high latitude to low latitude, which also is a cooling effect. So heating flux, ocean advection work together to produce the cold bag I showed you earlier. So actually we calculated this, I don't want to show it here, we calculated also it's obviously it's intensify will increase the heating flux and also the ocean advection by Ackermann transport, which both can cool the ocean. It is. Next, we focus on the South Ocean. The people in PhD, many people like Sylvia and work on this South Ocean. We see that large warm body or South Ocean. So the question is, what caused this? So from our paper, we argue with AMOC. Okay, you can disagree, you can agree, doesn't matter. But our point, this is due to the AMOC. Okay. So, okay, in order to prove or at least demonstrate our hypothesis, we need to show a little bit of ocean circulation in Atlantic Ocean. Atlantic Ocean circulation basically have two components. One is in the so-called North Atlantic deep water circulation, so water in high latitude and convecting into deeper ocean, and also in South Ocean that also is convecting over there, the so-called Antarctic bottom water. So in order to study such kind of longer term scale variation, you have to define the index. Somebody so-called this metric. We define the AABW by minimum of the global overturn stream function between 60 degrees south and 80 degrees south. Okay, so with this definition, then we can take a look at the relation between this and this. And here's the result. The top panel basically shows that here is the AMOC. AMOC as defined earlier, like Bill asked the question. And then this is the AABW. You see the relation is very high correlate. What this means? This means when your model AMOC is weaker, then AABW is stronger. So it's out of phase relationship. So this is consistent with the people from Le Mans. So I know that the broker over there, he published okay. Let me finish. He published a paper a long time ago shows the paleoclimate shows AMOC and ABW is out of phase relation. One is stronger, another one must be weaker. Okay.
So how do you define the AMOC between 60 and 80 stars?
No, AMOC is in north between the maximum. Okay, first answer. AMOC definition is a maximum stream function between 20 degree north, 60 degree north, below 500 meters. For the ABW index, we defined over South Ocean, which is a minimum global overturn stream function between 60 degree and 80 degree below 3,000 meters.
But in 60 and 80 degrees south?
60 degree, 80 degrees. Yeah.
But I thought that you would have you wouldn't have density gradient because it goes around the Antarctica, so you can define it. Is even a stream function there?
No, it's a global. It's a global stream function. Yeah. It's a global. Okay. So actually, there's too much information here. So AMOC, if you define normally the integrate between the east and west, right? Ocean you have a boundary, right?
Yeah,
however, for this one you don't have a boundary. Just the global ocean you integrate from west and make a circle to the here. If you have a land, then continue going on. It's no boundary. So this is so-called global median overturn circulation. What you said here is that you said you have east-west boundary is so-called Atlantic median overturn stream function. This is the global mean circulation.
If you define a density gradient to define the stream function, if you integrate to the same place, you have zero.
No, you're not there. Not there. You integrate, you calculate same as AMOC. Only difference is this over global, and another one is from east-west boundary. Now this is not new. Now people doing that. When you see the later other people paper, you see that stream functions have two types. One is AMO Atlantic median or AMOC stream function. Another is called global overturn stream function. So it's different. So you can go to our paper to take a look how to calculate it. Okay. So okay. So we're talking about the auto-field relationship between the AMOC and ABW. And the low panel shows the ABW and at T-by over South Ocean. So you see when the ABW is stronger, the positive value is larger, which means when you Atlantic, it's Antarctic bottom water is stronger, your ocean model by over South Ocean will be larger.
But
so,
stronger, you mean?
Yeah.
Warmer? Or
yeah, the warmer. You see that if you this is the ABW stronger, right? You move here, the number is stronger. Then your model by is larger. So next question is why this happens. So the question is this: we need to take a look at the mean state over South Ocean. So here we want to analyze here with two data, not a core data. People call the product. This is soda and or the popular soda, and also that another data set we show here is global, here is the Atlantic Ocean. You see that the surface is cooling and the subsurface is warm. Other models show that ABW will be stronger, which means the convection is stronger, and the mixing is stronger. And this kind of increase in mixing will make surface warm. This is basically this extension, okay? Then next, we also perform the intermodal EOF analysis over South Ocean. So panel shows a spatial pattern for isolated band, and the low panel shows a PC mode. The red color is PC1, and the blue curve is ABW index. I showed you earlier. So basically, the whole South Ocean is warm, consistent with the model I showed you earlier, and the correlation is also high, negative 0.5. Then we like in North Hemisphere, in South Hemisphere, we also calculate regression. So what we have a PC mode, right? I just show you time series as PC mode, and then we calculate regression of the PC1 mode onto the 200 millibar J% height and the sea level pressure over South Hemisphere, and the low panel shows the surface wind shear. So the pattern here, I want to emphasize over Atlantic Ocean, have a South Ocean have a strong easterly wind anomaly, because in the mean state, in this part, the wind is a westerly wind. So this east wind anomaly means the wind is weaker, the westerly wind is weaker. So this wind is weaker, still have two effects. One is where in reduced northward Ekman transport, also decrease latent heating flux. So both effects were warm the ocean over South Ocean. And then later on, the local ocean atmosphere feedback can continue amplify the warm body over this South Ocean. And this, okay. So next topic is this. As I said earlier, and model by over Southeast Pacific farther model are almost 20 years. That's not zero problem over there. Most people develop a process, bigger program to try to fix the problem, and most people emphasize the local process. However, you see that this warm by that we have a cold by over there. What we argue is that the relationship between this, which means if we model is by here, this model by will produce warm by over there. So the similar situation for this, the over Southeast Atlantic Ocean is because cold by over the West Africa monsoon region. So next we try to take a look at this result. So the top panel basically shows the SST by in tropical North Atlantic Ocean, and this is SST by in Southeast Pacific. And you see that correlation is also negative, very significant. What does it mean? This means when if your model, you can predict, okay? If your model, no matter which not matter, if your model has a cold by over tropical North Atlantic Ocean, then this model by over TNA region will produce warm by over Southeast Pacific. This is the message we got. And this is during to summer and during to fall. Of course, the question is why this happens. Actually, the physical mechanism is very simple. Because in tropical Atlantic Ocean, they will have the water circulation, or another water, Hadley circulation. This Hadley circulation can try and connect tropical Atlantic Ocean and the Southeast Pacific. This is we produced this result in our another paper, which is published in 2010. So this is the mechanism for this. So basically, this is a summary. Okay. So what we show here is that IPCC model, which people also call CMAP model, and CMAP5, similar to the AMO, AMOC, basically the reasonable good. However, the details are different, okay? So, but also we show that CMAP5 is better than CMAP3. Second one is what we show here is early people only believe AMOC can produce AMO. However, we show here that the interaction over there. In one part, AMOC can produce the change of the ocean temperature, which is called AMO. Over here, so if AMO in warm sea also can produce, can change the AMOC. This is why your model can produce the oscillation on the multi-decade time scale. And next conclusion we get here is we found the common pattern not all, almost all IPCD model, global SAT bias. I don't want to repeat it here. That basically in North Hemisphere it's cooling, in South Hemisphere it's warming, no matter which model. And there may be some particular model not this, but 80% of your climate model shows this kind of SAT bias pattern. And this pattern, why this pattern, what we argue is when we submitted this paper to Nature climate change, that whole 3 reviewers there, 2 reviewers said, okay, this is very good. And the 3rd reviewer said he does not believe our result. So anyway, so he believes with global bias is not due to AMO, it's due to something else. So, but finally, we convinced this reviewer to let us publish the paper in Nature Climate Change. So our next conclusion is this. Okay, our prediction for future is dependent on model. No matter what, you have to use a model to make a prediction. Either on seasonal time scale, interannual, multi-decade, we need a model, couple model. So of course, a model that every model has bias. So most people focus on fix your model bias. So what we show here is that if you want to improve your model, you cannot only focus on regional process. You have to consider remove effect. As we show here, North Atlantic Ocean can influence the Southeast Pacific model. And the last one is also people study AMOC. AMOC will be happy. AMOC is very important. So in other words, if you want to use your couple model to predict future, or no matter under global warming and under nature variability, you have to simulate the AMOC. If our result is correct, we can conclude if your model cannot produce AMOC, then your model out. This is the bottom line for our paper. Thank you very much. And if you have any question, we can discuss together. Okay.
I have a question about the sampling one. So you said in order, there's a positive feedback when the AMO is AMO, and then there's the next feedback on the other hand. But in order to have an oscillation, both effects need to overshoot the anomaly from one phase to the other phase. For example, if you have a stronger AMOC, then it will lead to a positive AMO. But the next feedback is not strong enough, and it just extends the positive anomaly to 0, which will not give you oscillation. So what are the possible physical properties that lead to this oscillation changes to
the detail is complicated, maybe because the ocean judgment is very important. Also delay. You have to have a delay time because when you have for example, if for any reason your AMOC increase, then this increase AMOC will produce stronger northward heating transfer, the warmer North Atlantic Ocean, right? So this thing is very slow time scale. This warm SAT in North Atlantic because amplitude is different, high latitude larger, low latitude smaller. And this is a warm SAT in not high latitude, low latitude will produce the difference of density gradient because AMOC depends on Miniano density gradient. So this kind of density gradient change, of course, after delay time will weak the AMOC. So the couple system tells. Anyway, the detail where each model is different, but this is the common feature we found. Not every model, also, but 80% of model behave like this. Some models do not have such kind of behavior. I believe we have 4 model, 6 model, is not like this. This is only 80% of model but this.
Also, I have a related question. You showed the AMO index has several spectral peaks at 10 years and 50 years. And what are the possible physical connections between this mechanism with
the different time scale? Yeah, this question I don't know. Is like for example, like ANSU. If you calculate the ANSU index, minimum 3, minimum 4, any index. If you perform the power spectrum you also show the many peaks over there. But there's one dominant, but 2 year, 3 year, which is so-called interadding. The similar like this. I believe here that there are many peaks over there, but which one is the most important depend on model. Like answer is also they have multi-decade time scale. So there's many peaks over there. Chris?
Yeah, Chunzai showed that most models get the AMO and the AMOC with 2 small amplitudes.
Yeah.
40 to 70 year time. And showing the biases that show up globally as a result of that. What's missing? What are the physics missing in the models if it's systematically not getting the amplitudes right?
Yeah, this is a good question. That when we submitted this paper to Nature Climate Change, the value will come back actually very smartly. Wang later I said this is very smart. He question similar what you asked, but he argued, okay, AMO see that your model, right? We're talking about not about observation. Your model, different model have different. For example, ocean model. We talk about ocean model, right? So some model have sea, the vertical direction have sea level, and this review argues the sea coordinate is very important. Not the AMO. Not the AMO is the stronger. Even you change the sea coordinate, we will change the AMOC structure. So the detail I don't know. Actually, nobody knows that. You only can guess why model is that. There's another way that okay, what we did here with we remove linear change. This is also not good because many people argue with global warming is not linear. You cannot perform linear change, right? But this is a very simple way to do it. You can argue this is not a good way, and many people perform many different, but the conclusion I don't know. This depends on how you look at it. Anyway, here we remove global warming by linear change. So some people argue this is not a good way to do it. But we don't have a good way because we don't know what kind of global warming change. So the simple way is the linear change. More? Thank you. Okay.
Wait. Let's do this first. Did you press stop? Stop recording?
Okay.